Where do we use reinforced concrete? We use it in frames, we use in foundations. Most certainly, you will not use any other material at all. No matter whatever kind of structure you have in foundations, almost certainly you will use concrete. Retaining walls, dams, water retaining structures, highways, and bridges as well. Even road pavements are made up of reinforced concrete. Some of the road pavements in the UK as well. Now, reinforced concrete beams. Is there any question up to this point?
Just one question.
Yes, please.
How does concrete behave submerged in water for a long time?
It's a very difficult question. How does it behave? It requires special additive. Remember that you can add lots of things to concrete to make it suitable for particular applications. So, for example, if you're talking about bridges and if you're talking about its pylons, abutments being submerged in the water, they will have some kind of special adhesive superplasticizers added to it to make it water resistant, to check its permeability. So for merging it into water, certainly we need special additives, and certainly we need special types of cements as well. Okay, we need rapid hardening cements when you're talking about underwater. Okay.
Hey friends, if you're new here, I am Dr. Jawed Qureshi, a senior lecturer at a London university. On this channel, we explore technical and human skills to help us lead more productive, happy, and examine life.
Okay.
What makes concrete fire resistant?
Yes, it's just the sheer nature of materials that we use in concrete. We use cement, we use aggregates. So aggregates is a kind of stone and sand. Stone and sand, these are naturally resistant to fire, aren't they? Because steel is embedded inside the concrete.
Yeah.
That's the reason that it is fire resistant as compared to steel structures. For steel structures, certainly you need coatings and other things to make it fire resistant. But for concrete, pretty much you don't need anything to make it fire resistant.
Is that why hotter countries tend to use concrete?
They do, yeah, that's the reason. And another reason is that because there's a lot of local expertise in concrete structure, there's lots of confidence in concrete as well. And also in some of the countries like Saudi Arabia, you would have sandstorms, very heavy sandstorms. So sometimes steel structures, they can't withstand that kind of abrasive nature of sandstorm. And also it provides the kind of volume, and the deflections are low as compared to steel structures. Especially for residential buildings, it is quite a good material. So two materials are really very important, steel and concrete. Other materials you can learn, but for structural engineering career, understanding how to design in these two materials is extremely important.
So do you use concrete? So in a big structure instead of bricks, why would you use concrete instead of brick?
Yes, it's a very good question. The reason we use concrete in large structures is that it is stronger than bricks. And then it provides a frame as well. By frame, I mean that each component of a structure is connected to each other. So if one component fails, other will take care of it. And ability to resist lateral loads as well. So if you're talking about bricks, you cannot go more than 3-4 stories. And the reason is that the lateral stability, wind and earthquake. And also another reason is that the ability to connect with each other. So when we are constructing walls made of brick, certainly there is a connection. We use ties and other things, but they are not as well connected as you would have it in concrete. When we cast concrete, when it acts as a single unit, when you have beams and slabs and columns, they act as a frame. So if one component fails, other components will take care of it, and then the entire structure is not going to fail. It's a kind of ability to be cast in a frame. And on the other hand, with brick and mortar, the walls are normally taking load from your slab. But in case of reinforced concrete, it's a kind of frame. So the load is transferred from slab to beams and then from beams to columns. You actually do not need walls. Okay.
Hi, Javed.
Yes.
I got a question. If the bridge is combination of steel and concrete, I just want to ask, which load would we consider in designing? Steel's load or the concrete's load?
It's a very good question. Thanks for that. So for bridges, when we have combination of steel elements and reinforced concrete elements, in that case we use Eurocode 4, which is code for steel and concrete composite structures. So for composite structures, there is separate code. I mean, loading is independent of any material, to be honest. So if you're using 1.35 GK plus 1.5 QK, that is applied to steel, that can be applied to concrete. But is that what you're asking, that what code do we apply, or
No, I mean to say like when we are designing the steel element of that bridge,
yes?
so we need to consider the steel design load. But on top of that, we are putting the concrete slab on steel
Yes.
element. So in that case, when we have to design the steel element, do we have to consider the concrete structure in design load?
Yes, definitely. So, for example, if you have concrete deck on top of steel beams, then you would say that load will be transferred from the concrete slabs to steel beams or steel trusses underneath. Okay.
Okay.
But if you are having elements, so for example, if you have a circular hollow column, and then if you're filling that column with concrete, okay, then how do you design it? Is that what your question?
Yeah, like I want to ask about the composite structures.
Yes,
Like,
excellent. I get your point. When you have, for example, if you have rectangular hollow section, or when you have circular hollow column, if you are filling that column with concrete, then there are special design provisions for that. Okay. And those special provisions are dealt with in various design codes, and they are termed as steel concrete composite structures. And this is one of my expertise as well. So I can talk about it for many hours. The reinforced concrete beams. Now this is a beam that is tested in a lab. Load is applied. You can see that it has developed some kind of cracks. This is the diagram. You can see that we have a neutral axis where we have zero stresses here. And then we have compression zone. This is simply supported. This will happen when you have simple supports. So in simple supports, if you draw a bending moment diagram, it will always be like this. This top portion is in compression. The bottom portion is in tension. In case of concrete, we normally say that, okay, that this zone is really not doing anything because the tensile strength of concrete is really negligible. It is 10% of its compressive strength. So we normally say that there is nothing here. This portion is taken care of by steel reinforcement. When you apply loading, then cracking, diagonal cracks are going to happen. This shows cracking. To avoid this kind of breaking at the bottom, because concrete is weak in tension, we put this reinforcing bar at the bottom. And this is the main purpose of today's lecture, that we want to design this bottom bar or tensile bar in singly reinforced concrete beams. So let us see what is happening. I think there is no sound in this video.
Yeah, we're not getting anything through.
Yeah, there's no sound, I think. You can see that load is being applied. And you can see that these cracks are developing when loading is applied.
What's the size of maximum of the crack?
What is the size of?
Crack.
I don't know what is the size, but they seem hairline cracks. So let us see what's happening. So the cracks are progressing, and suddenly you will see that this will fail. The experimental failure load was 42 kilonewton. Now, how do we work out the moment, the internal moment? It is worked out by force in the compressive zone times the lever arm, or it can be said force in steel times lever arm. So lever arm is the distance between these two forces. So this is creating a kind of couple. for this beam to be in equilibrium, the force in compression and tension, it has to be balanced. Otherwise, it will not be in equilibrium. So naturally, it's not going to be in equilibrium. The reason is that because concrete is so weak in tension and so strong in compression. So that's why we add this reinforcement at the bottom. And then FC is force in concrete, Fs is force in steel. And moment is Fc into Z or Fs into Z. So remember this point. And remember that this portion, the strength of concrete in this portion is ignored because concrete does not really take tension at all.
Thanks for watching. Don't forget to subscribe for more practical insights into structural engineering and beyond. Until next time, stay curious.